Dear students, in this video we will try to learn the complete description of a particle in a one-dimensional box. So we write particle in a one-dimensional box. This is also called as potential well problem. Potential well. So we imagine a one-dimensional box of length A, 0 to A, which has infinitely high potential at its two ends. Infinitely high potential. That means V is equal to infinite. V is equal to infinite on both sides. That way we can also visualize this box as a well in which the particle is staying. Now, how do we define the different regions of this box? Of course, it has three regions, two regions outside and one region inside. We know that the particle can only be found inside the box. So the wave function psi has to have a finite value. That means it cannot be zero inside. But we have chosen this particle that its energy is only kinetic and not potential. So V is 0. Outside, of course, we know this particle cannot pass through these walls. So the probability of finding the particle outside is 0. In that case, psi is 0 in the outer regions. So let us recollect it again. If V is infinite, psi is 0. And when V is 0, psi is not 0. Now, let us write the Schrodinger wave equation for this system. We know its general form is del square psi plus 2m by h cross square E minus V psi is equal to 0. We can modify it as d square psi by dx square because the particle is moving in one direction only, x direction. So we write it this way, plus 2m, since we know the energy is wholly kinetic and not potential, so we write 2me by h cross square psi is equal to 0. Alternately, we can also write it as d square psi by dx square plus k square psi is equal to 0. But we have chosen to write this k square equal to 2me by h cross square. Now you can easily identify this as a second order differential equation, and we know for such equations the solutions are given as, of course, the standard form is d square y by dx square. For y we have psi here, so psi can be written as a sine kx plus b cos kx. Two constants will be involved because it is a second order differential equation, and we know its general solution is of this form. Now, let us apply boundary conditions to this equation. The boundary condition is that when x is 0, psi is 0. So, when x is 0, sine 0 is 0, cos 0 is 1, psi is 0. So, 0 is equal to b. Of course, cos 0 is 1. It's b into 1, that's b, and this entire term is 0. Now, we substitute this b equal to 0 back in this equation and we get psi is equal to a sine kx. So we have applied the boundary condition. Boundary condition. Now we have a second boundary condition as well, that at x equal to a, this psi is again 0. That means at x equal to a, this psi is again 0. What does that mean? A sine ka is equal to n pi. Because, it's 0. If this is 0, that implies that this Ka has to be equal to n pi. Ka is equal to n pi. I wrote it in a hurry. So we know that sine vanishes for all n pi. So for all n, sine of n pi is 0. So Ka is equal to n pi. So this K is equal to n pi by a. Or K square is equal to n square pi square by a square. Now, we have already obtained this k square. We can equate these two. So when we equate, it is n square pi square by a square is equal to 2me by h cross square, right? From here, we get the value of E. E is equal to n square h square by 8ma square. Now you can assign different values to n. If n is equal to 0, e is equal to 0. But this is a very trivial, ordinary solution because n0 also means that this wave function is 0 and we know that it's not 0 inside. Therefore, we start the values of n from 1 only. So n is equal to 0 is not a possibility. We start giving values to n from 1 and onwards. From 1 and onwards. Now, let us try to see what should be the form of the wave function. So we knew that this wave function was like this. Psi is equal to a sine kx. So psi is equal to a sine kx. For this k, we'll put this value that psi is equal to a sine. For k, it is n pi by a into x. Now we are not aware about this a, but in a previous short video, I think we have already normalized this wave function to obtain the value of a as under root 2 by a. So you can go to that video again. So this comes from normalization of the wave function. Now, if you put it back, psi is equal to under root 2 by a sine of n pi x by a. This is the final value of the wave function for a particle in a one-dimensional box or a particle in a potential well with infinitely high walls at the end. So that gives the complete description of the same.